Because position, velocity, and acceleration are vectors, when considering two-dimensional motion, where the velocity might have both a horizontal and a vertical component, or the position or the acceleration might as well, we need to be very careful how we label them and how we work with them. So for example, if I have generic motion, let's say motion that's got both vertical and horizontal, I'm going to use the variable r to indicate that it's just relative to some origin, but not necessarily horizontal or vertical. It could be horizontal, could be vertical, but this is generic, allowing me to consider multiple cases. And I'm going to place a vector sign over it so that I know it is a vector and I need to consider its components. In one-dimensional motion, we haven't needed to do that because everything's along the same line, and so we can indicate direction, be it just pluses or minuses. But now we have to say, well, how much of that r is in the x direction? How much of that r is in the y direction or the z direction? This could be for three-dimensional motion as well. All right, so our kinematic equations would then take the form and look like this. This is r final equals r initial, okay, plus v as a full vector times delta t, okay, plus 1/2 a as a full vector times delta t squared. Okay, so now I could look at this and think, well, vectorially, what does that mean? For simplicity, I'm gonna cut off this. I'm gonna say acceleration equals 0, so we can just look at just these three vectors added together. And what that would say is I'm going to add these two vectors to create this one. And so, for example, I could have this be my initial position, full vector, and this would be my change in position. I could draw that maybe, let's say it's like that. So this would be v delta t, okay? And my final would then be, if I was here, and this is how I changed my position, then I must be over here, which means relative to this origin, I am now over here. Here's my r final. Okay. Now, a question you might ask is, well, I was this far away. That would just be a scalar, just how far away from this, doesn't matter what direction. I could ask, well, how far away am I now? I'd want to find out how big that line is. Okay, now there are multiple ways of doing this. One, you can use what's called law of cosines to figure out the size of this, if I know the size of that and the size of that, and then the angles they make. But since we're going to be focusing on motion that can be broken into components, like horizontal pieces and vertical pieces, we're going to do it by adding up their components. So for example, just generically, let's suppose I have this relationship. A vector A, and these not necessarily physical, this is just math right now, but we can relate it just like over here. Vector A plus vector B equals vector C. Okay? I'm going to rewrite that also to say, well, what if I'm looking for vector A? Vector A would be equal to vector C minus vector B. Okay? So A plus B equals C. Well, that's, let's say if this is A, some generic vector A, okay, and vector B is something like this. Okay, so my marker's having some issues here. Well, how do I draw vector C? How do I do it? The process, as we saw here with this physical example, that the additional part is from the original part. So I place the tail of the second vector being added to the first on the tip of the first. Okay, so the way you do that with vectors, as long as you don't rotate it or change its length, you don't change its size. Where it exists in space doesn't matter. A vector is defined solely by how long it is and what direction it points. So as long as I don't change that, I can move that up here and get it like that. That's now vector B. And vector C then goes, the result goes from the tail of the first vector to the tip of the second vector. That would be vector C. That's the generic way of adding them graphically. Okay. Now what about the second step? What if we want to find vector A? Well, C minus B is the same thing as C plus a negative B. And what does a minus sign mean in front of a vector? Well, if B means a direction plus a magnitude, then minus that just means the other direction. It just means opposite direction. And so negative B looks like that. And so I'm going to take vector C and add to it negative B to get A. And so if I take negative C, which I'll redraw over here, so here's C, I add negative B, trying to draw that as accurately as possible. Then A goes from the tail of the first vector to the tip of the second vector. And that's how I'd find A equals C minus B. Okay, that's how we do it graphically. Now we'll move on to a case where we have components. So